catalog. Cool. So the Fermi Large Area Telescope, maybe I can stay here. Okay. The Fermi Large Area Telescope is a space telescope orbiting the Earth, and it has been used to survey the sky since 2008. Every 3 hours, it can survey the entire sky, and it measures gamma rays from 30 MeV up to over 300 GeVs. And with more than 15 years of data collected, it has been used to identify over 7,000 gamma ray sources. Now, the Fermi collaboration releases the data catalog of gamma ray sources in the form of the 4FGL catalog, and we have reached the tier, the data release 4. And it includes mainly exogalactic gamma ray sources with over 4,000 exogalactic gamma ray sources, about 600 galactic sources, and over 2,000 unassociated gamma ray sources. That is to say, sources which we have been able to identify, and they are indeed resolved, but we don't know exactly what they are. So they could either be extragalactic gamma ray sources, galactic gamma ray sources, or even something else. And so one might wonder, is there space for dark matter among these gamma ray sources? In fact, if dark matter interacts, it annihilates or decays, it may produce standard model particles that interact and produce gamma rays. And we might be able to measure these gamma rays from Earth. As such, even if a source is mainly comprised of dark matter, we might be able to observe it in the form of a gamma ray source. And this is what I want to try to do today. So I want to try to identify if there are some dark matter sources among the unassociated gamma ray sources which we have already measured. A galaxy like the Milky Way may host several structures, including dark matter subhalos. In this image, you can see a simulation of a Milky Way-like galaxy, and over here, circled in white, are some dark matter subhalos. Now, if a dark matter subhalo is heavy, say with masses over 10 to the 8 solar masses, it can host stellar formation, and we can observe it in the form of a dwarf spheroidal galaxy. There are a lot of people studying dwarf spheroidal galaxy. They have gained a lot of interest from the dark matter community, but today we want to do something else. So even though these are very luminous objects, there might be other dark matter subhalos which are much lighter, with masses from 10 to the 6 to 10 to the 8 solar masses, and in principle they would be much more abundant, so there would be many more of them. This kind of dark matter subhalos, on the other hand, cannot host stellar formation, and as such we would not observe them in the form of regular galaxies. And so we call them dark satellites. If these dark satellites have a gamma ray emission, this gamma ray emission would be extremely faint. And in fact, we have never measured a dark satellite. On the other hand, if we were able to observe a signal from a dark satellite, it would be a very strong hint to the particle nature of dark matter, and it would be probably the first hint of a non-baryonic gamma ray source. So they're still undetected, and so if they exist, they must be either unresolved, so they're a mixture, they are inside a mixture of gamma rays that we don't know how to treat really well, or if they have been if they have already been measured, they are not currently identified. This means that maybe it is possible that they are among the unassociated gamma ray sources measured by Fermi. And this is what we're going to try to explore today. So we want to search if there is a dark matter population of dark matter subhalos among the unassociated sources measured by Fermi.
Aurelio?
Yeah.
Wait, so is a dark satellite just a dwarf that's lower than 10 to the 8 solar masses?
They're not really dwarfs. So they are so a dwarf spheroidal galaxy is a regular galaxy. It is mainly dominated by dark matter, but they have stars inside. While a dark satellite would be an object which doesn't have stars. So they don't emit mainly visible light.
Right. So like you said, no one's ever seen one before.
Yes.
So how do we know like from the 8 solar masses is where they start? That's like the max. Like why can I not have a larger solar mass? Just because they would create baryons as well?
Yeah,
I mean,
exactly.
What makes 10 to the 8 is just a cutoff where
yeah, it's more or less the cutoff. Or they get it from simulations, like these kind of simulations of stellar formation. Yeah. So what we're going to try to do today is first try to understand why some of these sources are currently unassociated. Why do we not know what they are exactly? And then we will try to see how we can study them. Finally, we get to some model building and then draw our results and conclusions. So first of all, how can we identify the type of a gamma ray source? There are several possible ways. For example, we can study the energy spectrum, the variability index, that is to say how much the flux or gamma ray changes over time. And then we could also use a multivariate approach where we cross-correlate a signal from different experiments, say an optical signal with a gamma ray signal. But today we will focus on the energy spectrum. In fact, sources of different populations in principle have very different shapes for the energy spectrum. And we could think of using this feature to discriminate, for example, a more curved source like an like a pulsar from a flatter source like an AGN. And in order to study the energy spectrum, we need to choose a common framework. And the common framework that we choose is to use a fitting formula like the log parabola fitting formula. In this formula, this term over here describes the shape of the energy spectrum. This term over here is the spectral index that tells us how hard a source is, while the beta parameter tells us how curved the source is. And this term over here is just a pivot energy that we can choose, and we choose it as 1 GeV. And this is the normalization context that fixes the overall flux. Now, we can expect sources from the same class to have characteristic distribution in alpha and beta. And for this reason, if this distribution is quite distinct, we might be able to define a model that does some kind of discrimination of these classes of sources by using this feature, that is to say, the distribution of the energy spectrum. And this is what we're going to do first. So we're going to try to discriminate different classes of astrophysical sources among the unassociated gamma ray sources. And then we want to test to see if there is an additional population of gamma ray sources that could be dark matter subhalos. But before we get to that, why are some gamma ray sources still unassociated? Why do we not know if they are extragalactic or galactic sources? Well, there could be several reasons. For example, if there is a very low photon count, we cannot say much about them. Or if they are very close to the galactic plane, the signal to noise ratio in general is going to be lower, so it is much harder to characterize them at all. Or furthermore, if they are closer to the galactic plane, there are strong absorption effects from the galactic dust and stuff that there is in our galaxy. And so since most of the optical up to soft X-rays photons are absorbed, we cannot use the regular multivariate approaches where we are comparing a signal of another telescope with gamma ray data. And for this reason, the distribution of the energy spectrum parameters, that is to say alpha, beta, and the total flux, is going to be quite different for associated and unassociated sources, just for this association bias. And this is something that we need to model properly if you want to do inference on the unassociated gamma ray sources. You can see this in a quantitative way by taking a look at this distribution. This is just an histogram of the parameters of the energy spectrum. And as you can see, the distribution for unassociated sources is quite different from that of the associated sources. And this is something that we need to take into account properly if we want to do inference on the unassociated gamma ray sources. But why is there such a difference at all? So first of all, it could be due to a class balance. So we have said that many of the unassociated gamma ray sources are closer to the galactic plane. So it is reasonable to think that maybe more of these unassociated gamma ray sources are of galactic origin. And since the galactic sources like pulsars have a different energy spectrum from that of the extragalactic sources, we can expect there to be a difference in the overall distribution of the energy spectrum. But it could also be possible that there is another class of sources entirely among the unassociated sources, and that would be dark matter. So if we want to understand if there is dark matter among the unassociated sources, we need to take in consideration this potential class imbalance.
I don't think I've understood what you mean by class balance.
So say that there are 80% AGNs in the associated sources. So the sources that we know, they are 80% AGN, 20% galactic sources. Galactic sources are more curved, while extragalactic are flatter. Then if you just take the same sources, but you put 80% galactic and 20% extragalactic, and you consider these as a whole, so you don't know what they are, you're going to see a different energy spectrum.
Sorry, did you flip the two or didn't?
Yeah, I flipped the two.
Okay.
So say that there are more, like 90%.
In the identified sources, we have a fraction E of extragalactic and a fraction G of galactic.
Yes.
Now you imagine that in the
So
So what's the scenario you're talking about?
So, well, most of the sources that we know what they are extragalactic because it is easy to characterize them. There is lower noise and they're,
Yeah, I know, I understand.
okay.
But, well, one thing that would have been nice is to have seen a sky plot of where the unassociated ones are. Because
Mhm.
obviously, your first impulse might be, well, if you're looking for new physics, throw away stuff in the galactic plane because it's too complicated.
Yeah, so what we're actually doing is that we are throwing away exactly the galactic plane. We're doing a mask around 10 degrees
Okay,
because that's very hard to characterize. So we are
Okay,
considering
perfect.
stuff over 10 degrees.
okay.
Yeah. And still, most of the unassociated sources are quite close to the galactic plane. And the ones that are far away from the galactic plane, they are generally very faint. So it is sources that we will characterize in the future, but just right now we don't know what they are. While the ones closer to the galactic plane, there is no guarantee that we will be able to classify them
Right.
with regular techniques in the immediate future. And
But
so if you're considering just the overall distribution, so you take just the parameters of the energy spectrum and you make an histogram like this one.
Right, right.
So this difference could, so let's make an example.
So the lower is beta, that was a curvature one.
Yes.
And alpha is a spectrum.
So extragalactic sources, very low curvature, galactic sources, high curvature. So this already tells me that probably there are more sources with higher curvature. And so why is that the case? It could be because there is an extra population of dark matter, because dark matter is expected to be curved, or it could be that there are more galactic sources. So this is something that I need to understand.
I mean, it seems normal that if. Right, with AGN, let's say, you're seeing to greater distance.
Yeah.
Whatever your two classes are. You'll see them to much greater distance than pulsars.
Mhm.
So it seems completely normal that you would expect your galactic sources to. I don't understand.
So
It's like you're using this as a diagnostic of whether.
no,
It
it
seems
is
like-
just that. So you want to make a statement on the unassociated gamma ray sources, and you don't know what they are. So likely they are of astrophysical origin, and I want to test if there is an extra population of dark matter. The extra population is curved. Dark matter is quite hard and curved.
That's gonna be your hypothesis.
Oh,
sorry,
that's
by
what we get from
extragalactic, you mean-
simulation.
When you say the extra population.
The additional population.
Yeah. The unassociated.
Yeah.
Or the dark matter. I mean,
So there are unassociated gamma ray sources. I want to
and the
test.
simplest model is that it's the same as the associated ones, modulo biases about what's easier to see and what's not easier to see.
Yeah.
So, and then there's the other hypothesis that they might be something new.
Exactly.
Right.
Exactly.
See that?
So many machine learning studies, what they do is that they train some model on the associated sources, and then they apply it as is on the unassociated sources. And if there are more galactic sources, you're gonna make a mistake just because your training data set was, with a different balance of sources. So this is one thing that we need to take into account. The other thing that we need to take into account is that since it is harder to measure the unassociated sources, and that's why they are still unassociated, there might also be some intrinsic effect on the distribution. Say they might be larger, they might be slightly moving the parameter space, depending on the capability of the experiment to correctly
I
reconstruct.
mean, the they here are the unassociated cases, not the ones associated with dark matter.
Exactly.
Just any of the unassociated.
Any unassociated source has so we can see that it has a different distribution. We need to understand why it is different. It could be because there is a different class balance, so more galactic than extragalactic, and it could also, or dark matter, that could be also dark matter, or it could also be due to some intrinsic effects. So our experiment has some kind of systematic effect. And these are two things that we need to model at the same time, and that usually people are not doing. So either they are considering one or the other, but this is the reason to do this work is that we want to include these two effects for the first time at the same time.
Okay.
And we model it, so we model a prior shift that is a shift in the composition of the sources, so more galactic, less galactic, and then a covariance shift, that is to say an intrinsic shift of the distribution in the parameter space. Okay.
You mean between the full population, including the unassociated ones, and just the associated ones? I get what you're saying. I
Okay. Cool.
hope I don't have to remember the terminology. Go ahead, good.
Okay. So this is how we model the prior shift. And I hope that this thing makes things clear. So the idea is very simple. We say there are different components, for example, galactic, extragalactic, and dark matter. And we have the distribution of this specific class of sources, that is the red part. And this can be the distribution of the associated sources or the unassociated sources that we still need to determine, but it is the distribution. We model the probability distribution of the entirety of the unassociated or associated sources as simply a sum of this individual distribution weighted by a prior probability that is basically the fraction of sources that there are. So this would be like 0.8 if 80% are galactic or extragalactic. And if we're able to write this model and we fit it to the associated and unassociated sources, we would see the effect of a prior shift in the fact that this prior weight is changing between one dataset and the other. And if we are able to write this distribution, we can immediately perform classification and say this source is this class of source with a certain probability by using the bias theorem. So we can make predictions for the unassociated gamma ray sources, actually making them not anymore unassociated. But before we can do that, we need to define the covariance shift. So the way that we define it is very simple. So we need to first model the distribution of the associated sources, and we do that by taking the data from the CAT, the FORGL catalog, and computing a kernel density estimation. This is a method to obtain a distribution given the data. And then we define a distribution of the unassociated sources as something proportional to the distribution for a specific class of the associated sources times a covariance shift model. In this case, the covariance shift model can be anything that we want. We choose the simplest one, that is a sigmoid. And the sigmoid has a nice property of keeping the domain of the distribution constant, but allowing for enhancing or suppressing some feature of the distribution. And this is something that we will need to fit to the data, as well as the weights of the distribution. And now if we combine, so this over here is the term that goes in red inside the distribution of the previous slide. So this would be this term. And then we can fit this model to the data collected by Fermi. And if we do that, this is what we get. So on the left panel over here is the fit of this mixture model to the associated sources. This is nothing new. This is just what you get from the source catalog of Fermi. And as you can see, well, there are mainly extragalactic sources with, maybe you cannot see it really well, but over here there are galactic sources.
Sorry, what is there seem to be black dots and black dots with white circles, or what are they?
They're all with white circles. It's just not
they're
to
not
have them
with-
overlap
And
too
they're
much.
the unassociated ones.
Yeah, so all of these sources over here are sources of which we know what they are. So they are all associated sources, and over
got it.
here
Sorry.
are,
Now I understand.
Yeah.
I have to compare the two.
Yeah. And over here is the same thing. So the black dots are the measurements, but of these objects over here, we don't know what they are. So these are the unassociated sources. And to these, we fit our mixture model.
And what's the pink and blue?
So in blue, here I am plotting the probability distribution of a specific class times its prior weight. And you can interpret the intensity of the color as the probability of a source being of a class or another. So in practice over here, the main color is red. So we can expect these sources to have a very high probability of being galactic, while the source over here are blue, and they have a high probability of being extragalactic. So just by taking a look at this plot, and actually you can have a more quantitative estimation by using the actual fitting formula that we obtain, you can perform classification in the form of astrophysical objects of the unassociated sources. And this is the first main results of our paper, that is to say, a classification of the unassociated gamma ray sources using a principal statistical model. But this is not everything that we want to do. What we want to do is that we want to test the possibility that maybe some of these sources have somewhat higher probability of being dark matter. And in order to do so, we need to add an additional component to the mixture model that accounts for dark matter. So if I want to obtain what is the probability distribution function of dark matter, I need to mix together a set of information about dark matter. First of all, what I need to have to perform a Monte Carlo simulation of the sky is that I need to know what is the flux of my dark matter source as a function of the energy, and I obtain that by connecting the astrophysical properties of dark matter that are contained into the J factors, that is an integral over the line of sight of the density profile of dark matter, and this basically tells us how many are the sources of dark matter and how bright they are. And I need to connect these to the particle nature of dark matter that gives me the shape of the energy spectrum. And this basically tells us what is the shape of the energy spectrum. All these things together give me what is the flux of the dark matter sources, but this is not enough. I also need to understand what is the detection efficiency of the Fermi telescope to a specific dark matter particle with a certain flux. And this is also another thing that we obtain through Monte Carlo simulation and by running the Fermi detection pipeline. Once we know all of these components, what we can obtain as a result of simulation is the number of dark matter subhalos given a dark matter mass, an annihilation channel. In this pilot work, we use the BB bar annihilation channel, and given also the annihilation cross-section of dark matter. So given these three parameters, I obtain the number of dark matter subhalos that I expect to observe in the sky and that I expect Fermi to be able to measure. And furthermore, I obtain the probability distribution function of the energy spectrum. So the same probability that I obtained previously for the associated sources, but for dark matter.
Do you know how robust to tidal disruption and other things the dark matter subhalos that you're looking at are?
That's a very good question. So
Probably for J factors.
yeah, so in this simulation, we derived the results both for the dark matter subhalo mass within the tidal radius, or, which is what I actually used to present the results, we base our result on the circular velocity, the maximum circular velocity of the dark matter subhalo, which is something that is better estimated. So this should not depend too much on tidal distractions, just because we are using the velocity and not the concentration of the dark matter. And once I have this, I can just add the dark matter distribution inside of the mixture. So over here, you can see a simulation of the dark matter energy spectrum distribution for dark matter mass of 100 GeV, and this value of the annihilation cross-section that I choose to have a nice idea of how things work. This is not actually the best fit parameter, but else you wouldn't be able to see it. So over here is a model where I've added this dark matter contribution. And by the way, by fixing this term, I also fix the number of dark matter subhalos, and fixing the number of dark matter subhalos fixes the prior weight of dark matter inside of the mixture. And this is how it would look like. So now what I want to do is that I want to leave this parameter as a free parameter.
I was holding back asking because I thought you'd explain it later, but a lot of the parameter space is already excluded from other searches where you larger, right. There's a question of why wouldn't you be seeing this annihilation, the galactic center, or in bigger dwarf galaxies and stuff.
Okay, so
you're gonna somehow.
This is something I wanted to comment later, but I will do it now because it's a good point. So dark satellites are not nearly as bright as dwarf spheroidal galaxies. So you expect the result that you get to be less constraining than those of dwarfs, but there is a catch. So most of the things that we see have the assumption that the annihilation cross-section of dark matter is velocity independent. So if you assume that that is the case, then you get very strong bounds for
I
dwarfs.
see your point though, if it's.
But this obviously has a different velocity. Yeah, So I will be drawing bounds for
Okay,
velocity
fair enough.
independent, but something that we want to do in the future is do also velocity dependent bounds.
There where you might have a chance of
Yes,
winning, but
so-
otherwise it seems very unlikely you'll win from
Yeah.
that.
Also, working with dark satellites is very interesting because if you see a signal that you say is dark matter from dwarfs, you cannot be 100% sure that it's not some let's say astrophysical signal because there are still stars, there is still regular matter. But inside dark satellites, there is almost no baryonic matter
Mhm.
because there are no stars.
Mhm.
So even if we saw for the first time a signal from dark matter form a dwarf spheroidal galaxy, we would probably need to look at that to be 100% certain that a signal is from dark matter, not something else.
No,
So maybe this is the future of precision measurements.
no, but it's a
So,
good point that.
yeah.
You are allowed to assume parameters that you might have thought. were
Yeah.
good.
So you don't get a strong bounce, but what you get is something that is very clean. That is my entire statement. And yeah, this is the bound. So yeah, as you can see, okay, this is our fiducial bound. And in this case, we are assuming point-like dark matter sources. That is because all of the unassociated gamma ray sources are observed by Fermi as point-like. We cannot appreciate the extension. But if in the future we were to be able to appreciate the extension of the dark matter sources, and or maybe with another experiment, this is what would happen, and the bounce would become much stronger. So if you think about
Sorry,
it,
I didn't get I can't read the.
oh, it's a bit small.
caption
So
very well.
this is to say that the J factors that we use in the simulation
For different
are
things.
for a radius, so the extension of the source that is 0.1 degrees, and they are derived for the maximum circular velocity profile. That is what I was telling him about. While these ones over here are derived by integrating the J factor over the tidal radius of the dark matter sabelo. And so if it is more extended, the source, you can expect to see brighter sources. But right now, since we cannot appreciate the extension, the most conservative and realistic bands are this one in black. Over here are some recent bounds that have been derived using, again, a machine learning approach to classify the dark matter sources. But to my understanding, they don't explicitly take into account the covariance shift, only a potential of prior shift. So they should be taken with a grain of salt. And over here are some other bounds that are often cited in literature that come from an entirely different approach where you, instead of trying to infer or simulate the number of dark matter sabelos, you just say, okay, I fix the number of dark matter sabelo to a somewhat reasonable number, in this case 16 because they choose so, and you say, okay, let's drive bounds on how much can be the annihilation cross-section. Well, yeah, of course, the bounds on dwarf spheroidal galaxies are much stronger. And so are we doomed? No, because we want to do velocity dependent annihilation, constraints on the annihilation cross-section. And this is something that we're already working on the simulations and on the analysis. So if you're interested, stay tuned. So to conclude, I just wanted to say some follow-up ideas. First of all, this was a pilot work. There are a lot of things that we can improve on. First of all, we should write a better distribution for the associated sources. So the better is this distribution, the more solid our results will be. And we could, for example, use normalizing flows instead of a KDE. And also we should make the covariance shift model more expressive, because right now the covariance shift model is constraining the region of the parameter space where we can apply our analysis. So we are using only about 400 sources out of the 2000 that we have. So there is still room for improvement to gain sensitivity. As far as extensions are concerned, this technique is extremely flexible. We believe that it is it can open a new way to analyze unassociated gamma ray sources. And so, well, first of all, I would like to derive bounds for the velocity dependent annihilation cross-section. That is one thing, but also you could think of applying this technique to other experiments, and in general, any kind of experiment which has unassociated sources in potentially any band of energy. And we are thinking of using it with LASO and IceCube specifically. Also, you can tailor this analysis to work with astrophysical sources. So say that you have a good enough understanding of the astrophysical background, you could use this analysis to make a statement concerning any kind of mysterious source. And in particular, we would like to use this technique to say something about the millisecond pulses closer to the galactic center. And finally, and this is something that I am extremely interested about, and I'm really thinking about in the next, over the past months, is to look for a population of dark satellites among the unassociated, the unresolved gamma ray sources. So to look for a population of dark satellites among the unresolved gamma ray background. And this is something that we could do using the deep learning and simulation-based inputs. So stay tuned. So to conclude, I hope I convinced you that dark satellites are interesting target to look for a non-baryonic signal, and that prior covariantship influence the distribution of unassociated sources, and that they are something that cannot be ignored. Furthermore, this is the first work that accounts for both of them in a clear and concise way, and so I believe that it can be something that we should look into more when we are trying to model the sources that we can detect, but we cannot really already classify. Thank you.
Any more questions for Aurelio?
In principle, you can extend this to other.
Could you repeat, make it louder?
Oh, yeah. In principle, you can extend these also to other like wavelengths, because you mentioned like gamma rays, where you can do it to like.
Yeah, so in any situation where you have a solid enough understanding on the background, so in this case, the background that we need to model is the diffuse galactic background and the isotropic background. But if you have an understanding of what is the background, you can run simulations and you can do this kind of inference.
For all possible.
See, yeah, I mean, as long as the feature of interest that you can use to discriminate between classes is the energy spectrum.
Can you go back to the two slides earlier where you made your extensions and stuff? No. 16, I guess is the number. You say dark satellite population among unresolved gamma ray sources. How would you do? I mean, isn't that what you're doing? I'm confused.
So
You're trying to imagine gamma rays coming from regular, just even more even smaller
yes, that's it. Yeah.
galaxies.
So the ones that we are considering now are over threshold sources. So they are resolved, they are detected, they are characterized, but we don't know what they are. Here we would like to test and see among the sources that we are not yet been able to measure individually.
So it's just all of the excess gamma rays.
So we did previous work with machine learning where we were studying the source count distribution function of gamma ray sources. That is to say, the number of gamma ray sources as a function of the flux of the source. And you can measure this quantity very under threshold, up to 2 orders of magnitude under the detection threshold. That is because you have statistical information about that. So the background is not really isotropic. There are fluctuations due to these unresolved point sources. And so when you factor in, so this was for fixed energy, but when you factor in also the energy dependence, and this is the new part that we're working on, then you would in principle be able to distinguish between a population of unresolved sources that have a certain energy spectrum, likely that of extragalactic gamma ray sources, and that of another population that is much more curved, that would be dark satellites. And this is what we are trying to do. But well, the simulations are very hard to make because you need to make sure that what you simulate is something realistic. So the hard part over here would be being sure about your dark matter simulations.
But when you say dark satellites, do you mean specifically purely dark matter satellites, or?
Yeah, they're just
uh,
blobs of dark matter, basically.
So it's not, I mean, another possibility is to say, okay, we have this population of toroidals and whatnot, which we can discriminate statistically from the extragalactic sources by the shape of the spectrum. And what if you imagine, the simplest thing to imagine is that continues down to lower luminosity.
That could
But
also
the
be a
shape of the
possibility.
spectrum is the same.
Yeah.
It's not a, maybe you, with thought, you would change the shape of your spectrum a bit,
Mhm.
but then you could just fit for that.
Yeah, we could also.
And
I
you
mean,
know, it had a galactic type template.
we could even, I mean, in principle, we could just use dark matter, general dark matter subhalos and find whatever fitting formula that makes sense for the generic galactic subhalo, and test for a population of dark matter subhalos among the unresolved gamma ray sources. That is a very viable option too.
I think maybe we're talking about the same
Okay.
thing, maybe a different one. I was imagining just, let's call it really low luminosity
Mhm.
dwarf galaxies.
Yeah.
Lower luminosity, but not with, with no contribution from dark matter annihilation. Right, because we do believe there are galaxies with dark matter that are very,
But I mean, this technique doesn't really rely on the kind of source that you are using. So the idea is that you have a main population that I'm gonna go on a limb and say they are extragalactic gamma ray sources, and there might be another population. And you can make this other population whatever you want. So you could make simulation where you have one kind of distribution that is extragalactic gamma ray sources, and then you put on top of that the simulation for low luminosity dwarfs, or you can test whatever other option you want. You want to do this kind of analysis for millisecond pulsars, you add the spectrum of millisecond pulsars. So
right, well, I think I feel like we're both saying the same thing, but
I think so.
like we think we're not maybe, but it seems like a very first thing somebody should do, and let me make it a question, have you already done this? Is to say, okay, there's all these unidentified sources, which they presumably identify as sources because they're over some threshold of the number of gammas.
Mhm.
What is that threshold, do you know?
So, okay, I don't have a plot here, but so you don't really expect there to be a sharp cutoff.
Exactly,
So you expect there to be a loss of sensitivity. So
But
let me-
somehow,
I can draw
there's,
maybe something.
there's two categories.
Yeah.
There's identified sources where they see some adequately bright gamma ray signal, and they see that there's something behind it, and they say, okay, I identified that source. Then
Yeah.
there's your unidentified sources, where they think it's a source because it's got enough photons, enough gamma rays from that direction. And then there's the diffuse background,
Yeah.
which is gonna be, after all, from some sources. Mostly, and those just have, just one. Not even,
So here, when I'm referring to the diffuse background, I'm just referring to the real diffuse galactic emission. What I want to probe is the unresolved gamma ray background. That is what you have once you remove the diffuse galactic emission and the point sources. Okay.
perfectly, but you could have point sources that have such low luminosity, you only get one gamma ray from it.
Yes.
So I'm trying to ask you, what's the cut on deciding you've got a point source? How many gamma rays? is
Okay,
the-
so in what the Fermi collaboration does is that they think they have identified a source. They compute a test statistic that is basically it is connected to the number of photons over the number of photons of the background. So they have a
and-
likelihood with and without the source,
Mhm.
and if the likelihood is over 4 or 5 sigma, they claim detection of a source.
Mhm.
But you don't need to know that to make a statement concerning the number of sources that there are, because you can also use a statistical approach, which is counting on average how many sources you expect to see. So
Yeah, no,
Yeah.
But it seemed like a very first thing that you might apply your analysis to was the explaining the unassociated sources. Well,
So what we have done, we can already do, and what we did is that we have all the unassociated sources, and we have a statistical classification saying this source is galactic, this source is extragalactic. And this source has this probability of being dark matter, probability being very low. So this is what we did. Something that you can do, of course, you can say, yeah, but which kind of galactic source is, or which is it, or which kind of dark matter source it is. Is it a low threshold, like low luminosity dwarf, or a satellite? That is something that you can do by extending this analysis with a bit more refined simulations.
Maybe another way I could pose the question is, supposing you weren't interested in detecting dark matter annihilation.
Mhm.
Maybe dark matter doesn't annihilate,
Okay, yeah.
but it's very interesting to know the population of these very, very light satellites. Is there a way to extend somehow your study to place a constraint on the number density of dark satellites? If you assume they have the same ratio of gamma rays produced, just because there is some gas and star around them. Maybe too little to notice as a real satellite.
I think that this is what you would like to do with the machine learning approach, because if you assume that, okay, these are very low luminosity, you might have measured some of them, but maybe you have not measured all of them. So take this quantity, that is the number of sources over the flux times s squared, because it's mostly s squared. So the stuff that we measure from the catalog does something like this, where of course it decreases with flux. It seems to go straight and then it goes down because we lose sensitivity. What we do with the machine learning approach is that we, of course, we reproduce this part because else the machine learning approach is not right. But we can also keep doing this measurement until much lower the detection threshold, and then here is, we don't know what happens. So this is when you fix one energy beam. When you fix the energy, if you leave the energy as a free parameter, then well, this thing would move left and right, up and down. Mainly, it would move diagonally.
By the energy, I mean energy of the photons that you're getting.
Yes, but and you expect sources of different classes, of course, to have a different energy spectrum. So in principle, if that is maybe the spectrum of X-galactic gamma ray sources, maybe the spectrum of another population would be something like this. And if these two have the same energy spectrum independence, well, there isn't a way to discriminate.
Right.
But if these,
Well, in the sense of the distribution of the sky, there would be some sort of correlation, right? If they're galactic, they're going to
Yeah,
be more associated with the galaxy.
Yeah, of
If
course.
they're extragalactic, you might even see
Yeah,
extragalactic.
so if if there is some sort of feature,
But
either
if there's a feature, then you're better off. Yeah.
or energy, so we think that there is at least, I mean, we know that there is a difference in the energy spectrum. So the matter is more curved, extragalactic sources are flatter.
Right.
So we expect to be able to discriminate even dwarfs, even under threshold dwarfs have a curved spectrum.
Exactly. That was exactly
Yeah.
the point I wanted to make. That it seems like it's a thing you should do just
Yeah.
for astrophysics reasons.
Yeah.
not
Yeah.
for others.
And this is something that I'm working on right now. And I believe that is interesting and fun.
Well, I think, yeah, the system is kicking us off, so let's thank Aurelio one more time.
Followed very well lots of results. But I guess they've been very exciting